Metric distribution, very similar to binomial distribution in the sense that there are criteria, and the only thing that differs from the binomial in a geometric distribution is the number of trials. All right, so I have the example here: roll a die until the number 6 appears, and keep a record of how many rolls it took before the 6 was obtained. So we're actually gonna do that real quick. Let me just get my calculator open. So I'm gonna roll a die. So math probability, option 5, 1, 6. All right, and integer values between 1 and 6. And I'm just gonna roll until I get a 6. All right. So I didn't get a 6 after the first trial, I got a 5. All right, so I'll just put my outcomes here. I got a 5 again. Finally, I got a 6. Finally. Not really finally, it just took 3 trials. If I wanted to determine the probability of this occurring, this particular set of outcomes occurring, I could look at it and say the probability of getting a 5, then a 5, then a 6. Or I could look at it as saying the probability of getting something other than a 6, followed by something other than a 6, followed by a 6. All right, so it depends on what you're looking for. In this case, we're only interested in the number of rolls it takes before you get a 6. So what we're looking at here is the event or the probability that you do not get a 6 times the probability or the event that you do not get a 6 given that the previous attempt did not give you a 6. And then in the last instance, it would be the probability that you get a 6 given that the previous attempt did not give a 6, given that the previous attempt did not give a 6. All right. Now, because these are independent events, the probability of getting a 6 is not dependent on whether or not anything happened prior to it. All right. So we'd be looking at this by saying, all right, they're independent events. I would be looking at this as a probability of 5 over 6 times another probability of 5 over 6 times a probability of 1 over 6. All right. So these two instances are the failures, with the final instance being success. All right. But it's dependent on when that 6 comes up. All right, if it comes up in the first trial, then you would only have to have 1 trial. If you get a 6 on the 17th trial, then that would mean that you'd have to have 16 instances where you failed before you have the 1 instance where you succeeded. All right. So that's a little bit of a taste of a geometric distribution, but the whole breakdown is, you can see it below. I'm going to show you how to do it in a calculator too. Each trial in the experiment must have only 2 possible outcomes, success or failure. So it's got to be binomial in that sense. The probability of success doesn't change from trial to trial. The trials in the experiment must be independent. All right. The variable of interest is the number of trials required to reach the first success. So if you think back to the conditions necessary for a distribution to be considered binomial, we would say fixed number of trials, fixed probability, independent events, 2 outcomes. So for this, it's variable number of trials, fixed probability, independent events, and 2 outcomes. All right. So that's the only difference between the conditions necessary to consider a distribution geometric rather than binomial. All right. So all of this is really just a breakdown of that whole process. All right. So if we look at the table, I'll just show you real quick. If we look at the table, we could say the probability of getting a 6 on the first trial. All right. So X would be the number of trials. This would be the first trial. This one would be the second trial, and so on. All right. So it would be a 1 in 6 probability. My first 6 coming up on the second trial would mean that I got something other than a 6 on the first trial, which would give us 5 out of 6 times 1 out of 6. 3 trials, so the 6 coming up on the third trial means I got something other than 6 on the first 2 trials, and so on from there. All right. So that brings us to a generalization model where n number of trials, all right, so on the nth trial, we would say that the probability is equivalent to 5 over 6 times n minus 1, 1 less than the nth trial, multiplied by the probability of success. All right, so 5 out of 6 being the probability of failure, because we failed on all of those n minus 1 trials until we succeeded on that very last trial. All right, so that gives us this relationship here, which kind of, I don't know, I've always looked at this and said, do we really need a calculator to do this for us? Okay. With binomial distributions, yeah, because it's got the combinations and all that good stuff in it. But if I were to say, for example, we want the first 6 on the 7th trial, I would be saying, okay, well, the probability of getting a 6 is 1 out of 6. All right, that's going to happen on the 7th trial. All right, so that's going to be the very last thing that happens. All right, prior to that, I got everything other than a 6, so 5 out of 6. That must have happened the first 6 trials. So 5 out of 6 to the 6th power times 1 out of 6. All right, so you get your probability, it would be about 0.0558. All right, so yeah, that would be 3 significant. But we do want to get to a point where we can generate graphs for this, whether it's in Desmos or the TI, most likely the TI. We could also come up with the mean and the probability of mean and standard deviation of a geometric distribution. There are rules for that, but we could also sort of invent that as we go. All right, all of that is kind of justified in the next little bit of instruction there on page 34. But let me just take you through in the table, or using a table method on the calculator, or in the calculator. All right, so the issue that you run into is, since it is a variable number of trials, we do have to account for the fact that there would be n trials. Right, so there's no cap to how many attempts that you can take when you roll a die. Right, so before you get the 6. Now there is some practical maximum where you would say, all right, well, I don't think I need to roll the die 17,000 times before I get a 6. It's probably, yeah, maybe I don't get it on the first 6 trials, but maybe I get it, 2 or 3 runs through the cycle. Maybe I just need like 36 trials before I get there. All right, so we need to have some sort of practical domain if we're going to come up with a distribution. All right, so when we do that, if I want to do a geometric distribution graph, we need a practical domain. All right, so the practical domain would have to go from, well, 1, the minimum number of trials that you could have is 1, to some number n, but you have to actually decide on what that number is. All right, otherwise the calculator is gonna break. All right, so stat edit in L1, let me get rid of all this stuff. In L1, I would use some kind of sequence. All right, but fortunately we're looking at integer values. So in L1, I'm going to do the sequence x, comma, 1, comma, whatever I decide on the n value. All right, so again, that's second, stat, ops, 5. All right, x, 1. I'll go to 36. All right, just so I have something there. The step value I leave blank. Again, the step value is just what increments I want to go by. I'm going to go by ones. All right, so that'll populate L1 with all the integer values between 1 and 36. All right, so again, that's second, stat, ops, 5. All right, it comes up, like you just saw, it comes up using the wizard, but then ultimately pastes it in as this. All right, but then for the geometric distribution, there's 2 ways to do it. So in L2, so these are the number of trials in L1, right? So if we want, we can just put the formula in, but there's also a geometric distribution command, all right? It's in the second vars, right at the bottom. Remember, A and B is your binom PDF and CDF. There's also geometric PDF and CDF, all right? So that'll give you the density, the probability density function and the cumulative density function. It'll give you the areas or the probabilities associated with particular values. All right. So as long as you know the probability and the number of trials before success, you could use this. I think it's such a common sense sort of approach. I'll go through that in a minute. I think it's if you know the formula, it's not a difficult formula. It's not like NCX, P to the X, Q to the N minus X. That's a pain to type in. You want a function built into the calculator to do that. Here, I look at it being like, okay, well, the probability of failure is 5 out of 6. I'm going to raise that to the N minus 1, but my N's are in L1, so I'll do L1 minus 1. And then multiply that by 1 over 6. Instead of looking for a command in a menu, I just kind of find it easier to just type the relationship in. All right. So 5, 6 raised, so caret raised to the L1 in parentheses. That's always a little bit of an issue. L1 minus 1. And then take that result and multiply it by 1/6. All right. Calculator follows order of operations to the T. So it's gonna take this 5 over 6 and raise it to the power first before it takes that result and multiplies it by the 1 over 6. So we're good there. Hit enter. Gives you all your probabilities, and you could see that the probabilities are they're definitely fluctuating in some capacity, but in an exponential pattern. All right, the idea being that we're looking at a decreasing function. If it were a function, it's again another instance where we're looking at discrete data, but we're evaluating it using a continuous distribution. Right? But if you think about it, the probability of success is 1 out of 6. All right, so if I make one attempt and I get it, well, it should be a 1 out of 6 chance. All right. If I take 2 attempts, 3 attempts, 4 attempts, whatever, you just kind of reason it out in your mind and say, well, if this goes too long before I get a 6, I'm going to start questioning whether this is a fair die. All right. Because it really shouldn't take too long before I get a 6. If I roll a die, if there's a 1 in 6 chance, it shouldn't take 7 is fine. If you get it on the 7th attempt, you're not like, oh, this die is it's a loaded die, it's a fake die. you're not thinking that. But if you go like 37, 38 attempts before you get the first 6, you're going to be like, what's wrong with this die? All right. So, and it goes for all the other values too. All right. So it makes sense that the probability is decreasing as the number of trials increase. So we're looking at something that would have a horizontal asymptote. All right. And in fact, we get to a point where around 36 attempts, the probability is so infinitesimal that it's to the point of almost being negligible. All right. But if we go beyond that, you'll see we're looking at something that's practically zero. All right. But the reason we do it this way is not to figure out the individual probabilities, because we could have done that easily. I mean, I did it already like 4 or 5 times. All right. What we can do, and by 4 or 5 I mean twice. So what we can do with this is we can create a graph. All right. And that would be a probability distribution graph. But the issue with a geometric distribution is it's one of the few graphs that's allowed to violate the standing rule for a probability distribution, where all the probabilities have to add up to 1. Right? And that's because there is an asymptote. In order to actually get a result of 1, exactly a result of 1 by adding up your L2 column, you'd have to have infinitely many values in your L1 column, which is not practical. All right. So if you actually get a 1, so second stat, math, 5, add up your L2. If you actually get a 1, then you must have gone so far in your L1 column that your answer rounded so close to a 1 that the calculator it defaulted to a 1 as a result. All right. But you can see here I'm getting a total probability of about 0.999. All right. So I'd have to go, if I really wanted to get to a 1, I'd have to go much further. All right. But again, in the nature of a geometric distribution, you'd have to go out to infinity. All right. So what I would want to do here is create the graph, second y equals, turn my plot on. The histogram is usually where I go with this. All right. So L1, L2. All right. That'll give me a relative frequency histogram. All right, which is interpreted as a probability distribution. All right, so zoom 9. The calculator decides how it wants to create the graph, and oftentimes that aligns with our interests, but clearly in this instance that's not the case. So I'm going to adjust my window. My X max, well, X was my L1 values. Those only went up to 36. All right, so I did a zoom 9. I did zoom stat. All right, and the calculator thought in its infinite wisdom that I wanted to go up to 71 for some reason. All right, well, let's bring that back down to at least 36, but I like to give myself a value on the high side. All right, so whatever my domain is, in this case a practical domain, I like to go 1 less, 1 more. All right, just to give myself a little window. A little extra cushion in my window is what I meant to say. All right, my X scale, I only want to go by 1s, all right, because each integer value accounts for 1 number on the X scale. X min, X max, I'm sorry, Y min, Y max, well, these are probabilities, so I wouldn't want anything less than 0. But again, if I want to give myself a little cushion, maybe I'll go like negative 0.05, something like that. The Y max, the probability could never be more than 1, right? But also, if I'm thinking back to the individual probabilities that made up my list, the largest one was 1 over 6, and it only got smaller from there. All right, so maybe I'll do, well, 1 over 6 is about 0.167, so maybe I'll go to like 0.2. All right, again, just giving myself a cushion. Then hit graph, and now I have a nice looking distribution, and again you could see the asymptotic relationship, whereas you go out in terms of X, the height is decreasing, approaching 0. All right, but you could also see that we would lose interest in this information after a certain point, perhaps this location here, which is probably around 20, because then, just to the naked eye, the heights of the bars are almost indistinguishable from the x-axis, all right, just based on the thickness of the pixels. All right, so after about 20, we kind of stop caring. All right, so it gives you a pretty good idea of the extent of the distribution and how far you would need to go before you were successful. All right, and that's good. This technique is really good for making a judgment on whether or not something is, in terms of like an occurrence, an everyday occurrence, is consistent with what should be happening. I tend to go back to sports, but the classic example is, actually, I think I have this example in the notes somewhere, but it was like Michael Jordan was a career 90% free throw shooter. And so he takes, like he's playing in a game, and he takes like 15 shots, and you're kind of looking at it as an off night, because out of those 15 shots, he misses 13, the first 13. All right. So he's going to typically take 15 shots, free throw shots in a game. So, for example, he's probably going to take a couple more. All right. So we would say, all right, well, what's the likelihood that he's going to make his next one? Now, if they're independent events, you would say, well, he's 90% free throw shooter, so 0.9. All right. But what we would do in the geometric distribution is look at the probability that he would miss 13 shots, consecutive shots, before he makes his first one. And look at that probability based off of a 0.9 success rate. And if that probability is substantially low, then we would say, right, he's due. He's due to make a shot, because his distribution needs to spring back to what it normally would be, unless he's on a severe decline. With athletes, it's a different story, because you never know. I mean, the road game, home game splits, those always have some kind of impact. But yeah, you can determine based off of what the distribution ought to be and where the outcomes fall within that current distribution, what's likely to happen next. All right, which is, I think, a pretty cool application. All right, but like I don't want to bring everything always back to sports, but you could kind of look at it like even something as simple as, weather, being late to class, late to school, late to work, whatever. Like if you're the kind of person who is just like, maybe you're late for school once out of every year on average. Okay, so like we'll call it 1 out of 180. That's your probability of being late. Then you would say, all right, well, knowing that you're starting a new school year, what's your probability of having perfect attendance for that year? Meaning, what's the probability that you would go through 180 days without being late? That would be geometric. Thank you. So that's a very simplistic example, but it's something, And so you think about like even something like your projects that you're working on. Like if you're struggling to incorporate probability into your project, you have the overall theme, the structure, and you're saying, okay, well, we got to get probability in there somehow. You could start thinking about things like, if it's a competitive sort of thing where you're going against one other opponent, like how many consecutive games would I have to lose before I win? It's a lot of applications in casino games. Those sorts of games a chance, because if you think about, I think I might have talked about it. It's called the gambler's ruin strategy. Yeah, so that's the one where you would want to make sure that you're making the appropriate wager. You're going to lose a bunch, but if you make the appropriate wager when you do win, that would pay off all your debt. You win the big prize, and then it offsets all your losses over time. All right, but knowing what the probability of like winning on your 30th attempt would be, as opposed to winning on your 13th attempt, that's pretty important, obviously. All right. So that's the geometric distribution. There really isn't much in terms of examples because they all just kind of boil down the same way. Anytime you're looking at something that seems almost binomial, but they're asking about how many trials it would take before a success is achieved, then we're looking at something that's geometric. Right? But every question is almost always phrased the same way. You know, here's a probability of success. How many attempts would you have to make before you were successful? Or what would be the probability of your first success being on the 17th trial or something like that? Right? So it's really just, I didn't see the point in doing like 10 different examples here because it would just be rehashing the same thing, right, over and over again. So anyway,